Okay, let's talk about magnetic forces and the right-hand rule. So, a moving charge in a magnetic field will feel a force F equals Q V cross B. It's a cross product. First off, note only moving charges even see magnetic fields. If I have some constant magnetic field here, let's say I've got some B that's pointing straight up here, meaning that direction. And I've just got some charge Q sitting here, and it's just sitting still. It won't even notice that magnetic field. There's no force on it. It doesn't even know the field exists. Only moving charges see magnetic fields. What if we have that charge moving though? So let's say I have it moving with some velocity vector v. And let's assume for now it's a positive charge. We'll do everything with positive charges for a minute, and then we'll talk about negative charges. Then that force is the cross product of V and B. And to do that, we follow the right-hand rule. So there are two different approaches here. You can do the finger way. V is your pointer finger, is V. B is your middle finger. V, B, and then the force will be your thumb. So I have to rotate my hand around until my pointer finger lines up with V, the velocity. So my pointer finger is pointing along V. Now notice I can rotate my hand all around, but V, I rotate my hand until my middle finger, because I'm holding them like this, like an XYZ plane. X, Y, Z. Rotate my hand until my middle finger lines up with B, that way. Then my thumb will point in the direction of F. So the force is coming out at us like this, out towards your eyeball. The way we show in vectors and out vectors, this would be a vector out towards your eyeball, just a dot in a circle, and an X in a circle would be in. We think of vectors like arrows, like bow and arrow. Think of an arrow coming out at your eyeball right here. It's coming out at you. What you're seeing right there is the tip of the arrow that has just now penetrated the board. This one is an arrow going in. Think about the back of an arrow with those feathers on the back. What we're seeing here is an arrow traveling away from us, and we're looking at the back of it. We're looking at the feathers. This is a vector flowing out, a vector flowing in. So in this case, V cross B would be F. Or another way to do this is the curly method. So point your fingers along V, curl toward B. V cross B is F. See, if I had my hand like this, V, and I try to curl them, I'm curling away from B. V, curl toward B. Oh, that didn't work. What if I have my hand like this? V, I curl it. I'm not curling toward B. B is pointing that way. My fingers are curling down into the board. V, curl my fingers. Oh, toward B. That worked. So I must have my hand in the right orientation. Then my thumb points in the direction of F. Okay, let's do a bunch of examples like this. What if we had a constant magnetic field that points out of the board? So here's B. And I have, oh, I don't know, let's say V is going down. And I want to figure out which direction F is in. So V cross B. If I want to do the three-finger way. I got to get my pointer finger here, pointed at V. So I have to rotate my hand around until pointer finger points along V. I want to rotate my hand until my middle finger now, remember I'm holding my hand like this, V, B, F. So I got the V. I don't know where my middle finger is going to go. It needs to line up with B. Oh, there it is. B is coming out like this. So V is down that way. B is out towards your eyeballs. Then my thumb is the final third one, F. That will point to the left. So my vector F, the magnetic force, will be to the left. These are all perpendicular, or let me say this, F is perpendicular to both V and B. And F is perpendicular to B. Now that just gives us direction. Everything we're saying here is direction. What about magnitude? Well, you may or may not remember how to find the magnitude of a cross product. We could just calculate the cross product, which is kind of a pain, or the magnitude of a cross product will be Q here in absolute value, magnitude of V, magnitude of B, times the sine of the angle between V and B. Okay, let's do another one. Let's say this time we know F and V, and we're looking for B. So let's say our force is this way, and V, try to be consistent here, was up. Which way was the magnetic field pointing? So V, B, F. I got to get this guy, my pointer finger, lined up with V, the velocity vector. Get my thumb lined up with F. Oh, B must be out of the screen here. So B would be pointing out of the screen. Okay. One more. Let's say, oh, I don't know. Actually, let's do two more. Let's say B points to the right. And let's say V also is flowing in the same direction. Completely parallel with B. Then I'm trying to do this game. I'm trying to go V and I can't. I can't point my middle finger towards B no matter what I do. Well, remember, magnitude of F is absolute value of Q, magnitude of V, magnitude of B, times the sine of the angle between them. What's the angle between V and B here? My angle was 0, radians or degrees. Sine of 0 is 0. There's no force. This moving charge moving in the same direction as a magnetic field doesn't even know it's there. There has to be some angle in between them, even if it moved in the opposite direction. If the angle between these were 180 degrees or pi radians, sine of 180 degrees is also 0. We wouldn't feel any magnetic force there. Okay, what about, let's do B pointing down into the board. And V, oh, let's point to the left. These are all good problems. You should try every one of these. Try this one on your own first. Figure out which direction you think F will point in. Okay, hopefully you've done that. So V, B, F. Point my pointer finger in the direction of V, and then I've got to rotate my hand around, trying to get my middle finger to line up with B. B is pointing into the screen. So V. Oh, there we go. Now we're lined up. There's B. My thumb points down. There would be F. Okay, now every one of these I've done, I assumed I had a positive charge. What if I had a negative charge? If Q were negative, we just get the opposite answer. We got a Q right here. He doesn't have an absolute value on him. If Q's negative, we just get the opposite force. You could do negative charges. We're going to have a bunch of problems this semester with electrons. You can do negative charges with your left hand instead. And then everything is the same. But I'm left-handed. And if I start doing left-hand rule for anything, I'm going to mess up and forget to go back to right-hand rule when I have a positive charge. So I tend to not do that. But here we'll do one both ways. Let's say we have, I forgot which color I was using for which. Let's say I have B pointing to the right, and it's a constant magnetic field. And say I have an electron moving down here. So we could use the left-hand rule. Negative charges are the opposite. So this is my left hand, point my pointer finger in the direction of V. That's down that way. I got to rotate my hand until my middle finger lines up with B. Well, this is really hard to get into this position. That would be like that. Then my thumb points down into the screen. V cross B. V cross B would be F. So F would go into the screen. Or, if you don't want to switch between left and right hand all the time, let's just do the right hand rule, and whatever answer I get, I'm going to flip over at the end. So V cross B. V cross B. B points that way. That's how I have to orient my hand in order to get these two fingers right. The thumb will end up where it needs to be. My thumb is pointing out of the screen. But it's a negative charge, so I have to take whatever answer I get and flip it over, which is into the screen.